right, here at Adafruit, well, my home actually. As it always is, we're going to be doing some electronics tonight. I've got this board bring up I'm going to do. I made a couple mistakes in this revA of Circuit Playground, which is cool. It's always cool, revA. That's your chance to forget things. And so we're going to be doing a little bit of board rework, and that's always a little fun. I thought I would show that off because it's real easy when you're just showing off, oh, everything's perfect, and like the design is like ideal, and I put it together and it just works. But when you have like slight little details and you have to actually fix stuff, that's where you actually show techniques. So I thought that would be kind of fun to show off. So we'll get right into it, and let's go to the overhead cam.
The future of electronic videos. Here, live.
Yeah.
Yeah. Okay.
Okay.
We got some surprises here tonight, because you can do scope cam along with overhead cam. But let's start off with this overhead cam.
Okay. Yeah, we're going to keep it simple. Yeah. Keep this nicely lit. Okay, so we've got our Circuit Playground board here, and this is the board that we've been designing over, hold on, let me get it to focus in really nicely. Oh, come on. You can do it. Okay. This is a board that we've been designing with EagleCAD. And I got the prototype back, and you remember I also put it together a couple of weeks ago, maybe a week ago. So we started the QFN. I finished up and soldered all the rest of the components in. And that's when I realized that I had forgotten to put pads on the back for programming the chip. Actually, I did put pads on the back, but then when I copied a board into a panel file, I forgot to take those with me. And so even though I have this like lovely board, I actually can't program it because I don't have programming pads. And I'm using an Atmel chip, which uses ISP, which is an SPI-like, SPI method of programming. But you know, we're not one to stop. I mean, I could have respun the board, and that would have been fine. But I thought, like, hey, we can pretty much get this going. So on the back, even though there's no pads for connecting to the ISP pins, the traces do go from the chip to the SPI accelerometer. And so there's these little vias that go through, and I can just solder to the vias, and that's how you get to the signal. And soldering to vias is kind of like, actually it's funny, it's like that's how I first did electronics. I was hacking up a PlayStation 1, and to get the mod chip connected, you solder to vias at some points. And the secret, in my opinion, to soldering to vias is getting 30 gauge silicone wire. This is like my favorite thing in the store. I kind of like everything, but some things I like a little bit more than others. So what's nice about this stuff is it's extremely thin. It's 30 gauge stranded wire, so you don't have to worry about it cracking as much as solid core wire wrap wire, which is what I used to use. And second, because it has a silicone covering, you can get it into small places and not worry about the heat of the soldering iron melting the covering. If you are soldering stuff that uses like a PVC cover, you'll notice it shrinks away as you solder, and so the exposed part gets longer and longer, which is kind of annoying. That doesn't happen with silicone. And also if you accidentally touch it with your iron while you're trying to get into a delicate spot, and you touch a side wire with the side of your soldering iron, you don't have to worry about it melting because it's silicone. So let's start. I'm going to start with, hold on, start with a green wire. I think this is the MOSI pin. I'll check later exactly which pin it is. And I'm going to pull up the board on my computer so I can follow the traces. Hold on, let me turn on the layers I want. Turn off values. Turn on dimension. And then, okay, so first up, let's do clock line. And the clock line, I'm going to do with a white wire. Oh, yeah, thank you. I'm going to do this with a white wire. And you should have really nice quality strippers for when you're dealing with 30 gauge wire. And I kind of forgot to bring some home with me, so I'm kind of using these not so great ones. You can do 30, but it's just, it tears a little bit. That's okay. Again, it doesn't matter as much with silicone wire because you don't have to worry about, like, it doesn't have to be as perfect. It's a little more forgiving. And then got my soldering iron, and I'm going to tin this point here. And then this one is this via. So I use 23 mil vias, or is it 0.02 inch vias. And so you can actually just sort of stick a 30 gauge wire in the via. And even though I tent them, so that if you don't tent your vias, like if you don't have a solder mask covering the via, this is of course a ton easier. But even if you're tenting the vias, the via itself is not doesn't have solder mask inside of it. So you just kind of melt some solder against it and just yank to make sure it's not moving. And that's pretty much, you have a wire connection. Okay. Next up, I'm going to do green, and I'm going to do the MOSI line. You want to highlight that on the computer? While I strip this wire. So that's this line here. And just going to do the same thing. And if you have different colored wires, it's kind of nice because you can have each signal be its own little color. It makes it a little easier later on when you're trying to connect it to something and you're like, wait, which one's which? Again, you can just stick the wire into the via hole, and then I just lift it a little bit. Oops. And melt some solder. And if it's tinned especially, it'll melt nicely. Yeah, this is just a technique. I mean, like, granted, is a technique that ideally you would never have to use, but sometimes you have to use it. Okay. Next up, I'm going to do the reset line. Actually, the reset line's pretty easy. Grab some yellow wire. Oh man, this yellow wire is just like slightly different thicknesses. Okay, well, I got it. Okay, so the reset line is, let's see which one it is. Is it this one? Yeah, it's this one. Okay. Oh, you know what? This has a little bit of a, didn't quite tin perfectly. Okay, that's good. So 1 second, I have to get in here to see exactly which via. Okay. Okay, so that's the reset line done. Okay, and then I want to do the miso line. I'm almost done here. Okay. Grab a little bit of blue wire, and this is pretty much the SPI lines. You have clock, reset, data in, data out. And then I need power and ground, but those are real easy to get. Don't worry about that at all. Okay. Yeah, it's such a joy to use silicone-coated wire. Like, if you've never done it, I really, really suggest. It's a little bit more expensive than plain wire, but like, it just does exactly what you want. Okay, so this is the last one. It's the meso wire. Hold on, again, I gotta get in here to see which one it is. It's really hard to see purple against purple mask, but this is the, yeah. Okay, yay. All right, so next up we need a power line. So that one's pretty easy. Use red. Okay, and then instead of going to a via, which I don't have to, I can go to a one of these gigantic power pads, which is kind of nice. And I'm going to flip over just to make sure I get the right one. So here's 3.3 volts. So I can just connect to this. Okay. And then, of course, I need a ground wire. And then likewise, I don't have to worry about connecting this to a via. I can just connect to this ground pad over here. Actually, I can connect to, this is a gigantic ground pad too, and that way I'm not blocking anything. So that USB connector. Okay, lovely. We got our fine little wires. I'm just gonna make sure that they're all tinned. Ready for the next step. Oh, and then there's one more thing I gotta do, but I'll do that after I put the connector in. Okay, so next up, to program this to an AVR, I need to, hold on, let me go to, I have to solder in a 2x3 connector, because I'm gonna be using a USB teeny. And the USB teeny has, this is like the oldest picture of the internet. It has 6-pin ISP connector. And instead of trying to plug those thin wires in, I'm actually going to just hook up a 2x3 header. Let's see, and then you can go to this breakout, which has a nice big picture showing you the pin out. So power, master out, data, ground, reset, master out clock, master in. And so if I solder this little connector, I can just plug it into my USB teeny. Now, when we're in production, you're like, well, why don't you just put like this connector on the circuit playground board? Well, I didn't really want to spend the space to have these headers. What I do is have just pogo pads on the bottom, and then I'll use pogo pins during production to program in the bootloader instead of having an actual connector on it. It's just a little bit easier and simpler. I mean, when you've seen us do teardowns, that's how people really do it. They don't usually, there's no connector, there's no JTAG connector. Instead, there's just a bunch of pads that you would pogo pin on temporarily, program in the board, and then release, because you only have to program the board once. Okay, so back to the overhead. Let's do, actually I'm gonna kind of put my wires away a little bit. We're going to do this up. So looking down, we're going to start with the top right pin, which is going to be VCC. Just solder that pin on. So that's pin 1. And then 2 pins down is ground. So get that we'll get that pin connected. Okay, we're a third of the way there. Next, let's do the reset line, which was, actually let's just do this pin next, which is clock. Okay, so white is the clock line, and that's exactly opposite middle. This thing's just going to dangle. But because I'm using silicone wires, I don't have to worry as much about like, oh, it's going to get shorted or damaged or melt wires. All right, good enough. All right, next up, let's do the one to the right of that, which is MOSI, master out, slave in. Master out, slave in is between VCC and clock. So that's the green wire. You should probably use a third hand, but I'm kind of being lazy, just holding this by hand. Okay. Next up, let's see, which wires do I have left? I have this wire here, which is reset, and that's yellow, and that pin is below the clock line across from the ground line. And that only leaves one pin left, which is this master out, slave in, or master in, slave out, sorry. And then we've got all 6 pins connected. Okay. Oh. Okay. So now I've got a nice 2x3 header. I mean, if I had the pogo pins, it would be a little easier because I'd just be soldering to the pads. But either way, I'd have to wire up one of these because I'm not ready to make a pogo jig yet. And then, I actually made another mistake in this board, which I realized right after I sent out Gerbers, which is kind of how it is, which is I forgot to do a pull-up on the accelerometer pin. So, the accelerometer, I originally had it only on I2C, and then kind of at the last moment was like, oh, you know what, I want to leave the I2C pins available for capacitive touch. So I quickly, this accelerometer can do either I2C or SPI, which is like one of the really cool things about the list 3DH. So I changed it from I2C to SPI, and then I was like, oh yeah, I need a chip select line to connect to D8. Then of course I was like, I forgot that, you know, it's going to now be, it doesn't have an internal pull-up on the chip select line, and so I will, you know, right now, actually I should, hold on. I'm going to remind myself that I need to pull up by just adding one right now. But since I don't really want to send out new boards, I'll just touch this wire, this pad to power while I program it so it doesn't interfere with the SPI lines that are used for programming. So I'm going to do one last soldering, and then I'm done. Okay. Okay, and then this line, I'm just going to trace it out. It is, hold on, I have to think about it reversed. Okay, it's this one here. So, no biggie. And then I'm also going to hold on. I'm gonna make some room over here. And just when I'm ready to do the accelerometer, I'll remove the wire. Okay. So, oh, wonky, but whatever. I'm just gonna get this working, and then revB will fix that thing, and then maybe a couple other things. Don't forget the pads. If I'm lucky, I'll get this done in maybe 2, maybe 3 revisions. That's not unusual to have a couple revisions. Once in a while, for a breakout board that's really simple, actually, no, I will keep this here. For a breakout board that's really simple, I will be able to do it in 1 revision, but it's pretty rare. Even the most basic breakouts usually take 2 or 3. Okay, so now, got the USB teeny. Going to connect it up. That's a pretty good sign. I got the glowing LED. You can kind of barely see it. So it's a good sign. I also have a backup one, but let's go to the computer. Okay, and we're going to open up shell and run a dude. No, sorry. Oops. Hold on. Just give me a second. I gotta power stuff up. And then, one second. Sure, I got the. Oops. Sorry, one second.
It's okay.
I have to.
I got stuff going on here that I want to do.
I get the. Okay. So I'm going to now go to my. Okay, so I've got Circuit Playground. I'm going to go to, in dev boards, I have a batch file that I made. Oh, not ABT, BAT. Oh, it's in, okay, I gotta remember where I put it. What's in breakout boards, Bluetooth, BLE, revB, got it. Okay. So in this folder, I have a batch file that'll, because I was programming the, these boards so often, well, that I was, I basically made a command file for me to burn all the fuses. So first command burns the fuses, and this basically sets up that there's a bootloader section that I'm going to be clocking it externally with 8 megahertz, set the brownout, watchdog, all that good stuff. And then, oops, sorry, I will burn in the Katarina Bluefruit Micro bootloader. And this is a bootloader that basically lets me, once I burn it in, I can remove the USB teeny and I can just program the Circuit Playground board just using the Arduino IDE without needing like any extra stuff.
What do you mean when you say burn the fuses?
Oh, it sounds like you're actually, like there's actual fuses, like chunky things. They're called fuses because they used to be like more permanent because it was like a one-time programmable thing. But these fuses are actually like little bits of memory. And there's some things that you want to set up that aren't just the flash code. Like there's the code that runs inside of the microcontroller, starting with address 0, that's just like set this pin to be an output. You know, turn it high, LED on, turn it low, LED off, read this register, set that register. That's your code, but the overall settings of your microcontroller you would do with fuses. And I can actually, there's a great calculator that I use called the embedded fuse calc. This thing is like the best thing on the earth. I've used this probably since 2006. It's great. And basically for every chip, because it's you can read them in the data sheet, but it's so confusing because the fuses are negative. Like to set the fuse, you set it to 0 because you're burning the flash. Non-burned flash is 1, and then when you burn the flash, it's 1. So for example, if you select the 32U4, for example, do you want to use the internal RC oscillator, or do you want to use an external one? And how long do you want to, wait after it's been set to like start up? Because like sometimes crystals need a little bit of time to stabilize. Those are settings like divide the clock by 8 internally. So you can have like a slower clock. You can clock with 8 megahertz, but it's really 1 megahertz. Preserve the EEPROM over chip erase. Do you want to have a bootloader? If you want a bootloader, how big is it? Is you want a 2K word, 1K word? Because you have to tell it how big the bootloader is. Do you want to have the watchdog timer always on? That's a safety thing. So you always have something checking to make sure that the program is running and not crashed. Do you want on-chip debug enabled? And so when you look at the fuses I set, hold on, actually, I'll just look here. So I set the L fuse to FF. So one of the coolest things is you can go down here and you can actually type in the fuses that you're like, because like you can reverse type them in too. D8, and then E fuse is CB, and then you apply the values, and you can see what I set it up to be. So it uses an external crystal oscillator, which is true, and it's 8 megahertz or higher, which is true. I don't want clock output on pin C4, C7. It's a kind of a handy thing if you want to have like it clock something else, or you just want to debug it or something. I don't divide by 8. I do have a boot loader. I have the boot reset enabled, and I have a 2 kiloword flash. I don't preserve the EEPROM through the chip erase cycle. The watchdog timer isn't always on. I might change that later, but for now I think this is fine. I do enable the serial program, and I don't use JTAG. I'm not using JTAG. I'm not using on-chip debug, and my brownout level detection is 2.6 volts. You want to set this to be like about a half a volt less than your nominal voltage. So my nominal voltage is 3.3 volts, so 2.6 means you have a little bit of buffer. I mean, the next highest one is 3.4, so I obviously don't want that. You don't want to have your bootloader, your brownout above your working voltage. So there's a couple different things here, and you can disable it, but if you have a bootloader, you should always keep it enabled. This is like the first thing I learned when I did the Zoxbox, because I didn't have a brownout detection. So I was like, whatever, I don't care. If you don't have brownout detection, what can happen is as the voltage drops, and it can drop just like on power up, or just like, if you don't, maybe the power's lost and the voltage drops, it can jump, the memory gets corrupted a little bit because it's running at a low enough voltage that like the chip basically gets a little confused, and then the PC pointer, the pointer to your current instruction, gets corrupted, and it jumps into the bootloader like in the middle, and then it like erases a chunk of your flash, because in the bootloader there's a little piece that says like, okay, I'm bootloading, erase the flash, and then program it with what the bootloader wants, what the USB interface wants you to program. So this is like the most important thing you can learn about microcontrollers. Always have the boot. If you have a bootloader, you must have, and even if you don't really, just have the brownout detection there, because otherwise there's this risk that it will jump into a random piece of memory. And yes, this is mentioned in the data sheet, but it's on page like 482 in a footnote. So like, yeah, it took me like weeks to figure this out when we were working on the Zoxbox. So anyways, always have the brownout detection when you're using a bootloader. How to boot enable, I don't need that. That's a little like, it's a switch that lets you do the bootloader. I'm always going to have the bootloader enabled. Okay, so now we learned all about fuses. I hope that answers the person's questions. It's a little settings file. Okay, where were we? Okay, so we burned the bootloader, so let's go back to the overhead cam. I don't need this anymore. Okay, so now you've got this nice pulsing LED. That means that you've got the bootloader programmed in. So I'm actually going to remove the USB Teeny, and I'm also going to, real fast, remove that wire that kept the accelerometer disabled. Okay, so now I'm going to plug this back in. So you've got this nice pulsing LED. I'm going to insert this here, and we're actually going to start bringing up this board. Now we know a little bit of it works because we were able to program it. So the crystal definitely works. The power supply, for the most part, works, you know, to some extent. This LED works. This LED works. So let's go back to the computer. We're going to start the Arduino IDE. Whoa. Just a couple of me. I'm just going to put away these wires at least.
Yeah, so keep in mind that's not bad. This is
Oh, sorry. I have to remember how to read the screen. Okay.
So if you go to your screen and get everything going, then I'll toss it.
Okay, yeah, get rid of this thing, and then I don't need this so much, and then I program the bootloader, so now, okay, we're down to the Arduino IDE, and so this is the board down here, and let's see if we can do this. So we're going to start with just blink, and I'm going to basically call this a flora, because that's actually kind of not a bad board to assume this is. Sorry, hold on. So I'm going to call this a flora. Eventually I'm going to have like a special line item for it called Circuit Playground, but for now, I'm calling it a flora. There is a couple side effects to that. The flora has RxTX LEDs. It doesn't, but it's the same chip clocked at the same frequency. Next up, I have to see which COM port this is. And COM port, it is 63. I'm using the Teensy driver for this. That's why it shows up as a Teensy. It's a generic driver. Okay, so let's try to upload some code, make sure all the USB is working. Okay, uploading, and then, yeah, now you can see the blinking LED. So that's good. So that's pin 13 is working. So let's make a new program. And we're going to call it Circuit Playground, and it's going to be our test program. So let's basically just go through and we're going to test each element of the board. And this will, you know, it's kind of good because it just gives us an idea of like, you know, what works, what isn't. But also, when we do our test procedure, this can be part of it. I don't know if it's going to be in this case, but having a program that tests every part of a circuit is a really good way to have a regression test. So like when you change something with your board, you can always go back and test everything. So let's start with the red LED. Red LED is going to be pin 13. Let's start with a serial. Have a serial thing. And then set it to be an output. And then the loop, we're going to turn it on. And then turn it off. And then we're going to have a little delay in the middle. So it's a fast blink. And then let's see how this does. I have to manually reset it because I haven't set the baud, the COM port. I'm going to set it now. Okay, so now you see it's blinking really fast. Okay, so we got that thing next. Next up, I'm actually going to test the NeoPixels. So there's 10 NeoPixels around it. There's 5 on the left, 5 on the right. So I'm going to just crib from the NeoPixel library because I like cribbing code. So include the NeoPixel library, create a NeoPixel item. And then for the pin number, I actually wrote it on the silk screen, which you can't maybe see on the overhead, but it's pin 17. Oh, hold on, I forgot. I wrote it over here. Pin 17 is this is the wire that goes in to the NeoPixels. Oh, that one. So set this up to be NeoPixel pin. We have 10 LEDs. Uses this pin. It's the GRB type, I'm pretty sure. NeoPixel 800 kilohertz. Right after we initialize the red LED, initialize the strip. And then for pixel equals 0, pixel smaller than 10. Actually, I'm going to do something different. I'm going to create a global variable, pixel n, which starts with 0. And then I'm going to say, OK, set pixel n to be all on. OXFFFF means all 8 bits of 3 colors, red, green, and blue, so all the way on. And then I'm going to increment it. This is different.
It's cool, right? Like, because you can see it on top of the IDE.
Yeah, as long as you can read
Yeah.
it.
Yeah,
I think you can.
Yeah.
OK. So not working. Set pixel. Oh, forgot to do strip show. You have to remember to tell the NeoPixel strip to push the data out. Let's see if this works. OK. Wow. So now we have each pixel light up in a row. I'm going to make that less traumatic. Set the brightness to 20. And then also when we get to, when it gets to 10, start over. And then also clear the strip. Yeah, that's bright. Oh my God. OK. So now you see just little LEDs. And then, of course, we can change the color to be, you know, red, for example. So that's kind of nice. You can leave that like that. OK, so it looks like all the NeoPixels are working as well. Although I actually kind of want it to be blue. Ooh, OK, that's nice. Nice blue colors. OK, so we got red LED going. We got these LEDs going. Next up, let's check out the switch and the 2 buttons. And then we'll go on to the sensors. So next up, we're going to, let's look at the left button. Actually, let's go to the switch first. Switch is on pin 21. And the way I set it up is there's no pull-up. It actually connects either to ground or power. So define slide switch pin to be 21. Set it to be an input. No pull-up. Actually, I'm going to start making little sections. OK, I know what I'm testing. Test, slide, switch. So I'm just going to read slide switch pin. And if the pin is high, that means it slid to the left. And then if it's otherwise, it's to the right. So this will just print every time it loops, but we'll also get to see the serial console.
This fuzzer thing is cool.
Yeah?
Yeah.
Yeah, I kind of like how it's in here in the corner. That's kind of cute.
Yeah, that's good.
OK, so now we're, so it's blinking. It says to the right.
Electronics, like if we do courses with Circuit Playground?
Yeah.
Like,
No, this is me practicing.
yeah, this is great.
So slide to the left, slide to the right. And then one of the things I can do is, for example, have that change the color. So maybe I'll make a new variable, pixel color, and then and start this with just set to 0 to start. And if you slide this to the left, then pixel color is green. And if it's slid to the right, it's red. And then actually I should change this to be pixel color, and then I'm actually going to put this below so that I don't start setting the color before the pixel color set. So I can start doing little interactive things, so it's like you don't even have to like look at the serial console if you don't want to. Okay, so it's red, and then I switch it, and it can go between red and green. So to the right, it does red pixels. Left, it does green pixels. So a little bit of interactivity. If I could flip it really fast, I could make it like Christmas themed. Because every time it loops, it'll change which one. Okay, so that's a slide switch. Okay, so next up, let's test out the buttons. We have 2 tactile buttons. Left button number 4, right button number 19. And now you might be thinking, for this one you definitely want to pull up, but actually I did something a little weird with this design. Now where'd the buttons go? For this design, I actually put pull downs on the buttons. And the reason I did that is because I thought, well, one of the things that beginners do get tripped up on a little bit is if you have a pull up, then it's like if digital read, and then they think like the action is pressing the button, so that would be the positive occurrence, where, as you know, if you have a pull up, when you press the button, it shorts to ground. I mean, I guess I could also have the button short to ground and have a pull up. I guess I could change that, but I thought like, okay, well let's just try this for now. Yeah, I'll probably just do that. I'll have it short to ground instead of, or sorry. Usually you have a pull up and you have the button short to ground, but in this case, it's shorting to power, so that when you press the button, the reading you get is the high value, and high value means pressed. It's a pedagogical decision. So that's why it's backwards from like every time I do it. So pin mode, left button input, and then input but no pull-ups. And then if you read it, then now I remember you actually just print out that the button was pressed. Likewise for the right button. Okay, so let's try these out. And you can open up the serial console. And then so you get that slide still working, and then when I push the button, let me shrink this down. If I push a button, it says, okay, left button pressed, and on the right side, right button pressed. So I don't know, I might change it to be the other way, where pushing the button shorts to ground. Still not sure. I do kind of like the idea of having, for Circuit Playground, it's not, I don't want to sort of teach pull-up resistors as much, because, I mean I do, but I don't want to have people set them because they're not really wiring stuff up. It's all inclusive, so I'm still not sure. Okay, so tested the microcontroller. The reset button definitely works because we pushed it. Left button, right button, slide switch. So next up, let's test the light sensor. We'll go and we'll do all the sensors and the inputs and outputs. So the light sensor is over here, and it's connected to analog 5, and it's basically a phototransistor. The more light that hits it, the more this conducts, and so the more current, and so this goes up. So more light means that A5 goes high, because there's more current going through, and current times R4 is a higher voltage. So that's kind of nice. I do like it when the sensor is, more light, higher voltage. Again, it's a pedagogical way of thinking of like, okay, what's easiest for people who are beginners to understand.
We're up to 47 minutes.
Okay, I'll tell you what. Let's do the light switch and the temperature sensor, and then we'll bail.
Yeah.
They'll be about, and if people have questions, you can ask them. So this one's really easy. Analog read. Light sensor. And I'll just print out the voltage, or the raw value between 0 and 1,000.
PW Dragon says, pull down are easier for beginners, no negative logic to explain. Good choice, Lady Ada.
Okay. 3. No, I mean, like, you have to think about these things, because, like, it's a little bit, it's like, okay, now you have 2 more components to place. Like, it would have been really nice if I could use an internal pull-up. And some chips have internal pull-downs, which are really sweet. But there aren't internal pull-downs on the at Mega 32U4. And so it's like, okay, well, I'm going to place 2 more components. Okay, so now we have the light sensor printing. And let's hold it up to this light, and you can see that the value is now like 1,000. So I'm holding it up to this little desk lamp I have here. And then when I cover it, the light sensor goes down to like 0. So it actually does a pretty good job of ranging from like low 20 or so. Here I can totally cover it up. From like 10 when covered up, and then when I release it to be about 200 in this ambient, and then when it's like super bright to be 1,000. So that's kind of nice. Next up, I'm actually going to do the accelerometer and the list 3DH. The list 3DH is not the cheapest. It's not. It is about 70 cents. There are cheaper accelerometers. However, this is the only accelerometer, the list sensor. I'm going to initialize it after the NeoPixel strip. And then I guess I'll just set the range. Well, okay, back? Cool. And then I'm going to use the sensor event, because I like it. It's normalized. It's actually in G's, not in meters per second squared. I gotta fix that. Good. So get an event, and then print out X, Y, and Z. Oh, I have to define the chip select line, because this is SPI. And it's, I remember because I just saw that wire, it's 8. Okay. So we're like almost through the entire thing. Still have the sound sensor, the buzzer, temperature sensor, but we'll see what we can get to. Okay, so this says meters per second. 1 second. I'm going to just change this to be G, because technically it's supposed to be G. Okay. Just picky about the print line. Okay, so now we're back, and so you see that there's it's printing out, and right now it says Z is 1G, X and Y are about 0. That's because there's the gravity vector pointing down. If I flip this over, it's going to be about negative 1G, and then depending on how if I have Y pointing down, Y is negative 1. If I point Y the other way, now it's 1, and then this is X. So this is 1G on X, and then negative 1G on X. So you can actually do fun like movement, accelerometer, tilt, action. And then I'm going to do one. How much time do I have till the end of the hour? Okay, well, let's just do the temperature sensor, and then I'm totally going to be done. For the temperature sensor, I'm going to be using a thermistor, and I forgot to order the thermistor part because it's not a stock part. So I'm going to really quickly just solder on a through-hole thermistor for my little kit. So I wanted to go inexpensive for this board, as I've mentioned. Even though I wanted it to be easy to use, and I have all this stuff built in, and I wanted to add a temperature sensor, but I didn't want to splurge on, you know, a TMP36 or something. So instead, what I decided to do is I'm going to go with a thermistor. And you know what? Like, thermistors are cheap, but you can get pretty good temperature sensing out of them. Like, and the nice thing about them is that they're not sensitive to VCC, because if you want to measure the resistance, you can do that as a divider. So, and if your AREF is the same as the VCC, it kind of falls away. Is that correct? Yeah, because you're just measuring if you have a precise series resistor, you're basically measuring the ratio against that. Okay, so I have a little thermistor sticking out here. It's through hole, but you know, whatever. We'll get an S-surface mount one later. And then I have a handy tutorial on how to use thermistors. And you can scroll down here. And this is a you know, kind of a large wire thermistor. Basically, you know, you're measuring the voltage out, and then, you know, if you're just measuring the resistance, and you know the series resistor you're using as a divider, because I basically have a resistor divider. Actually, I'll show it really fast. So this is the resistor divider. So this is the NTC thermistor, and then I have a 10K 1% over here. 10K 1% resistors cost nothing, so it's like you can definitely have a high precision. Also, 10K 1% thermistors are very cheap. They're only like 4 cents. So this whole thing is 5 cents, and it's like 1% precision, which is really nice. So you basically just, you can get the resistance by just measuring the ratio of the ADC against, you know, the AREF, which is the same as the VCC. So I'm going to also just gank this code so I don't have to retype it. So the series resistor is a 10K 1%. And then I'll just take all this. And, you know, personally, you know, I was like, oh, you know, how, like, is it so much better to use an all-in-one analog output temperature sensor? And it's like, in this case, you know, it doesn't. Like, it is nice to have a chip if you just measure the analog voltage, but in this case, like, I'm going to be able to hide the math in a function. I'm going to have something like circuit playground object, and then like dot get temperature, and I'll just give you the temperature. So I just have to define thermistor pin. I'll do that over here, and then it was a 0. Okay. And let's see what it says. Okay. So it says right now the thermistor reading is, I'll stop the scrolling, about 536, which means the thermistor resistance is about 11K. And then as I put my finger on it to heat it up a little bit, you can see the thermistor resistance is going up to 13K. And when I let go, it drops back down to like 12. So they're very, very fast. Thermistors are very fast. And also they're very, like, the amount of resistance delta you're getting is quite high. I mean, just me touching it on the epoxy body is enough to give me like another K of resistance, which is 10% change, which is quite a bit. And then I'm not going to go to the details of the Steinhardt equation, but basically it's not linear. You have to use a little bit of a function, a little bit of math to use the resistance to calculate back the temperature. I have all this kind of math done for you. So I'm just going to grab it. You kind of have to know the nominal resistance, and you have to know the beta of it. I know for a fact that the beta is 3950 because it's basically the through-hole version of this surface mount resistor. And then once you have the reading of the resistance, you can, I'm going to close all these windows. Once you have the reading, you can do the math of taking the reading, dividing it by the nominal resistance, which is 10K in this point, taking the log of that, dividing by the beta coefficient and B coefficient, adding 1 plus the nominal over temperature Kelvin, it looks like, or sorry, convert to Kelvin, and then you take the inverse of that, and then you subtract back to get into centigrade Celsius. And so we'll just see if we can get it to print out the current temperature. Okay. All right, so right now it's saying the temperature is 23 degrees C, which is pretty good. And if I touch it, oh, actually it's going down, which makes me think I have, oh, you know what? I must have the coefficient backwards. But it is moving. Hold on, wait. Yeah, I must have the negative coefficient, so it should be going up instead of down. So that just means I have, the code is for like a PTC instead of NTC, and I have the opposite one. So I'll look that up. I also actually look up the beta, because I'm pretty sure it's 3950, but I'm not 100% sure. But it is reacting, so that's good. Yeah, I wonder how I swapped that. Oh well. All right, well, it got pretty close. Okay. Well, I have all the sensors sensing. I think that's pretty cool. Okay. It's 23 degrees in here.
All right.
It's a little chilly. Okay, so I'm going to look up whether this is because I just got this out of my bin. I'm going to see if this is the wrong, yeah, because if I'm touching it, it's going down. It's probably my thermistor codes for a PTC, and this is NTC, or if that's NTC, this is PTC. Temperature coefficients for great justice. Okay, so we're going to go, but when we come back, we'll next time we will maybe finish up this sound sensor, the buzzer, maybe write a test program for this. And I'm definitely going to spin up another version with that pull-up resistor and also the test pads on the bottom. That's my next step.
Okay.
This is a nice little thing.
Another video broadcast. No one got hurt.
No, why would
Everybody's welcome.
Ow! Just poke myself in the face. All right, we got working hardware. Well, this is exciting. I mean, like it's coming along. I think probably second or third revision this will be done, and then people will see it in the store. Oh, and I forgot, you also have the capacitive touch capabilities. I forgot to test that as well.
All right, well, tomorrow night.
Maybe. Every night is electronics night here at every night is electronics night here at Desk Ladiata.
Apparently. Okay, we're outie?
I'm outie.
Let's get out of here. Okay, say goodbye.
Goodbye, fellow Americans. I don't know.